yeah, I'll just quickly show you this, and I'll put a link somewhere to this. But I mentioned, yeah, with this kind of transfer learning thing, the idea that these different kind of layers learn different features. And there's been quite a lot of work to kind of try and represent or try and visualize rather what those different layers look like. So this is one kind of example of that kind of process of trying to visualize layers. So yeah, there's quite a few different examples, but I guess the illustration at the top is quite nice just for showing you what I meant with this kind of edges and these kind of fairly basic shapes that some of these layers are able to learn. And I think intuitively you can kind of reason about how some of these kind of visuals would be quite useful for a broad range of tasks. And these are the kind of things that, you know, pre-training on ImageNet will help you with. Other question was about, there was a question about whether you can see which images are mislabeled. So there are various different ways in which you can do that. If I can remember. So yeah, within this FastAI library, you have some kind of some methods for looking at your results, and that's something that's covered a little bit more in the next notebook as well. So in this case, you might have seen one of these before. This isn't very helpful at all because we have two labels, so it's not that difficult to know which labels are getting confused most of the time. But yeah, this can be really helpful when you do have more labels to see which ones are getting confused. And that kind of goes back to this this kind of labels discussion that I mentioned of how that can actually be quite an important thing to get right. So I'm working on this other project at the moment, which is kind of trying to detect different types of pages in manuscripts. And in that case, some of the information you get from this confusion matrix can be quite useful because the mistakes the model are making when you kind of look at the images are actually quite reasonable ones for it to make. And often what you might kind of pragmatically decide to do at that point is if two labels are kind of very hard to visually distinguish from each other, you might just decide that you should just kind of merge those two labels together, or there might be some other kind of thing you wanted to do. The other thing that I quite like about this is you have this way of looking at the top losses. And let me just zoom in a little bit here. You can see here, hopefully, you have this, you have these 4 bits of information. You have the prediction the model made, the kind of actual label that it should have guessed. You have this loss, which I mentioned was the kind of internal measure of how wrong the model was, and then this probability score. So basically what this top losses tries to do, or it does do, is it will usually show you the results where the model was basically most wrong. So where the kind of, it predicted very confidently that it was one thing, but it was actually something else. And again, that can be quite a useful way of kind of digging into what kind of mistakes a model is making. And I think this can also be really useful for flagging up when something might be a problem with the data, or with the labels again. So in this case, the prediction was illustration, and it says text only. So yeah, it's a little bit hard to see with this, but I'm not sure if that's an illustration. That's just kind of smudge, but you can kind of see why the model might think that this is an illustrated advert. Again, this is predicted as illustration and text only, and arguably this is, you could see why this looks like an illustration. So I kind of annotated these images and kind of had a quite crude rule that anything that I kind of deemed fancy typography didn't count. It had to be a kind of illustration of something, but there are quite a few edge cases where it's a little bit hard to say. And I think that's also, I guess, particularly, yeah, I guess maybe not particularly. It's important in a humanities context where often you're dealing with more ambiguous categories. But I think more broadly, quite often you will have these edge cases. And the particular kind of model architecture we're using today has a kind of tendency to confidently predict one label. And the other thing is that if you set up a model in this way, it can only ever predict illustration or text only. So if I show this, this model like images from Star Wars or pictures of dogs or anything, it will predict it's an illustration or text only. It won't say, I don't know what this is, or I haven't seen this kind of thing before. So yeah, this again is probably, it really depends on what you're trying to do and what kind of data your model is likely to see, how much of an issue that is. Because in this case, you know, if you kind of have this model and you're kind of using it, you can probably be fairly confident about, most images fitting into one of these two categories. And then maybe you're kind of willing to accept that there's a little bit of edge case. But in other examples, this ambiguity, might make this kind of classification approach slightly too crude, really. So yeah, there's various other ways in which you can kind of dig into the results. So what I will quickly do is, so this is the second notebook, which these first two bits, let me just check. Yeah. These first two, or first three cells rather, basically do the same things we did before, just to get things set up in terms of the data and installing this FastAI library. So I'll maybe come back to that question a little bit later on. So yeah, what I think I will try and do, because I think we don't have that much time left and I want to leave time for kind of discussion, is I will probably go through this fairly quickly and just try and explain at a high level what this notebook covers. And this is kind of a reminder of what we saw before, this kind of overview of the process of kind of creating a deep learning model. And again, in this notebook, we work with data from this Newspaper Navigator data set, but we work with slightly different images. So this time we work with visual content that's basically predicted as being photos. So the other thing that I think I mentioned at the start was to kind of understand the data we're working with and the potential missing or inaccurate information. And one of the nice things about this data set is it gives you this kind of summary broken down by each label of how well the model did. So you can see that the advertisements were actually the kind of best performing category. The other thing that you can probably see is that there was quite a lot of examples of those. And if we compare that to photographs, that's quite a lot lower. The thing I would say about this this kind of score here is that the way in which you kind of measure the performance for these computer vision models, where you predict this kind of bounding box, is a little bit different to how we did it in our notebook. So because you're not just calculating whether it predicted the correct label, you also want to predict how close this bounding box is to where you kind of annotated that bounding box to be. And what that means is that sometimes these scores aren't always that representative of what, when you look at the predictions it makes, you think, oh, actually that looks pretty good, but the score might not kind of match that. So I guess that's just a little thing to say. Sometimes these metrics, you have to be careful about what it is that you kind of care about, and they don't always get captured that well in these metrics, and it's not always that easy to come up with a metric that will capture how well the model is doing. So I guess the important thing in this notebook that we do, which is different, which is the thing I just touched on, was instead of putting images into one of two categories, we now use this slightly different approach where instead of putting things in these categories, we assign them labels. And let me see if I can jump straight to, actually that's going to be a bit too far down, but yeah, I guess the broad difference between those approaches is in this kind of paragraph here. So with this classification approach, basically everything belongs in one of the categories. Whereas with the labeling approach, things can have one or none labels or more than one label. So the kind of analogy we've given here is you could classify, if you're going through some old family photos, you might classify the photos as being color or black and white, and it's quite clear most of the time that those images fall into one of those two categories. But you might also want to kind of assign labels to those photos. So in that case, you might have a photo that has many labels. So you could be labeling all the people that appear in the photo. Or you might say this photo has a landscape in it. Well, actually, the example here is that it doesn't have any labels because all you're labeling is people. But I guess the important distinction here is that these labels are a lot more kind of flexible in whether they're applied or not. So the model in this case can just say, I don't think any of the labels appear in this image. So I'm just going to go, I think, through this first part, and then I will skip through the rest. But this kind of notebook goes into a bit more detail about this kind of idea of exploring the data before you start training the model, which is something in the previous notebook we didn't really do. We just kind of took the data and assumed that it was fine. And in particular, to try and get a sense of how the labels are organized within our data. So I'm not going to dwell too much on this code, but we kind of work with this this library from Python called pandas, which is for working with tabular data. So data that you would open in Excel or some other kind of spreadsheet software, you can often or usually load in this pandas software. And this is usually then stored inside this kind of thing known as a data frame. And yeah, we've already seen a little kind of preview of this in the previous notebook, I think. But you can see here, this looks quite similar to what we had before, where we had this kind of file with our image. And in this case, we have this label, and you can see some of these have just this label human, and some of them have these two labels. It's a bit hard to see here, but these are kind of separated by this pipe symbol. And as you can kind of see, we have kind of 2,000 examples in this data set. So I didn't really talk about in the previous notebook how much data you need for these kind of computer vision tasks. And I guess the slightly annoying answer is that it really depends on what you're trying to do. But I guess broadly speaking, in this kind of example, this would probably be considered quite a low number. But sometimes, you know, with quite a limited amount of training data, you can still do useful things. So yeah, I guess the annoying answer is it depends. But I guess the other thing that at least my approach would be to try it out with what data you have and what data you can easily collect, and then kind of assess from there whether it is doing you know, terrible, or if it looks like with a bit more data, the model might actually be able to do what you're asking it to do. So this kind of notebook goes through a slightly convoluted process of splitting out all of these different labels. So I'll kind of skip over some of these details. But the important point that I think I want to point out here is the kind of distribution of these labels in this data set. And I think this is kind of quite important, because in the previous notebook, we had an equal number of adverts which were illustrated and text only. But you can see here that we have a lot more images containing humans compared to these other categories that are included in this. So we can again potentially get a better sense of that by kind of plotting this. And this kind of imbalanced data set where you have a lot more of one category than another is something that I think often doesn't come up when you're doing kind of intro tutorials to this topic, but I think quite often in the real world, the kind of data that you have will often end up looking like this. So it's quite important to be kind of aware of both that this can happen and some of the considerations that you need to take into account when data starts looking like this. And I think the bit that I just wanted to touch on was this idea of metrics. So in the previous example, we had this accuracy measure. So as I kind of said, that was basically some kind of ratio between correct predictions and the total number of predictions. And in our previous example, that worked quite well. But when we have some data that looks a lot more like this, this kind of accuracy measure starts to hide quite a lot of information potentially. So the example given here of quite an imbalanced data set where you have kind of 99 examples with label A, and for label B, we only have one example. So as you can probably already see, if a model just always predicts A, it's going to do pretty well. So if you kind of train the model on this data set, you would quite easily get this kind of 99% score by just predicting this single label. But you can probably already see that that's not particularly useful. And I guess also depending on what these labels represent, sometimes you'll really care about what this B label is, because that's the kind of rare example that you might want to identify out of this kind of broader data set where you kind of expect certain things to appear. It's this kind of anomaly that you're actually wanting to pick up on. So yeah, very briefly, I guess that's the first thing to kind of consider when you have a data set like this, is that this accuracy measure will often not work very well in that scenario. So often in that case, there's kind of other metrics that you can use. And one of these is this kind of F beta score. And this kind of gives you some kind of way of getting a better sense of the precision and the recall of the model. And this F beta combines those two different measures. So as you can kind of probably get a sense from, also the naming of these things, this precision score gives you a measure of how precise the model is. So basically the model's penalized for making wrong guesses, whereas this recall measure penalizes missing examples. And the kind of balance and trade-off between these two really depends again on what it is you're trying to do. But this kind of score gives you some kind of average between those two. So often this works quite well for a data set like this at giving you a slightly more realistic picture of how the model's doing. So I probably will have to rush through a lot of this section, but the only other thing that I think would be kind of nice just to show you. So this kind of section works through the kind of process of loading the data and creating the model in a little bit more detail. So this probably looks quite familiar from last time. So this is kind of nice thing about this FastAI library, is that even when data is kind of arranged in different ways, the kind of building blocks for constructing one of these data loaders is often quite similar. So in this case, we have this from data frame method instead of from CSV, but these things are quite similar in other respects. And just to kind of show you what is kind of going on inside this photo data thing where we store this. So one of the things that we looked at last time is this kind of viewing this batch. But the other thing we can kind of do is to actually look at the inputs to our model. And I said before that this was, basically a bunch of numbers. So we can do this one batch, and this will basically give us one of these batches that I mentioned before. So in this case, 32 images and 32 labels, and we store these in this X and Y variables. And we can use this thing in Python to tell us kind of what type these X and Y objects are. So yeah, if this is the first time you're kind of looking at this, this might look a little bit strange, but hopefully this kind of bit is kind of makes some sense, that you have this thing called tensor image. So you probably can guess this is some representation of an image. And then we have this tensor multi-category, which again, if we kind of look at our labels, you can see that this is kind of this multi-category where we could potentially have multiple labels or none. So this is what kind of inside this FastAI library, how these bits of information are kind of being represented. And we can kind of confirm that this is the length we think it should be. So 32 examples of each. And then, yeah, the thing that I kind of claimed before was that these kind of images end up as a bunch of numbers. So this 0 thing here is basically grabbing the first of these 32 images. And the kind of nice thing about notebooks, which I probably should have mentioned, is that if you kind of have this last cell, if there's a way in which it can be represented in the notebook, it will kind of print it out for you. So this is quite a useful way of being able to kind of dig around and see how things are kind of represented or what things look like. And it's not super easy to see from this what this actually is, but this is basically the tensor, or the kind of matrix of numbers representing the image. And it's a little bit easier to see if you kind of print out the shape of this. This probably starts to look a bit more reasonable. So this is the kind of shape that we kind of mentioned before. And then this 3, you can probably guess is the kind of the channels. So in this case, because this is a RGB image, this represents each of those channels. So this is essentially what the kind of images end up looking like for the model. And again, looking at the first label, it's not super easy to kind of read from this what this means, but if you kind of go back to the fact that we have some labels and they can either appear or not, you can kind of see that this is basically a representation of that. So when there's a 0, the label's not there, and then 1, that particular label does appear. So yeah, I think that bit is, I realize I've rushed over it, but I think this can be really important, not just within this fast AI library, but if you kind of get into this subject more, kind of these models can be quite hard to kind of put together in some cases, and often kind of being able to dig inside and seeing how things are represented, kind of what shape things are, can be quite useful as a way of trying to debug issues and try and also get a better sense of, you know, what's actually happening inside this model by kind of digging around at, you know, how these things are actually represented to the model. So I think I'm going to rush over this now. So a lot of this kind of repeats what we did in the previous notebook, but goes into quite a lot more detail. The thing that we also kind of cover in this notebook in a little bit more detail is kind of, yeah, this thing that I showed briefly in the last notebook of trying to dig into how well a model is doing. And in this case, trying to dig into how well a model is doing on particular labels. So I mentioned before this idea of you know, choosing labels being important, and also this idea of, you know, whether labels accurately capture the kind of visual information that we're showing the model, and also this kind of idea of unequal distribution within the data set. So this is kind of a model that ends up doing quite well on this particular task of predicting if there's a human in the image or not. But it does pretty badly at detecting if an animal is there. And I guess, you know, one way of explaining that is just that there's far fewer examples of that particular category. But I guess going back to this idea of labels, the other thing that I think is slightly tricky about this category is this animal label. For us as a human, it's quite easy to kind of reason about. If we see an image of an animal, we can quite quickly identify it as such. But it's actually when we kind of dig into what those animals are in this data set, there's kind of quite different animals that have visually different appearances, and actually potentially asking a model to predict this kind of broader category of animal from those examples is kind of asking it to do something that's quite difficult. So we might want to think about whether that's actually a kind of suitable label to get the model to predict on. So yeah, I think I'll wrap up there, and leave a bit of time for kind of questions. I guess it depends on what you mean by that. So there is, let me see if I can, this kind of, yeah, I guess there's this idea in computer vision and deep learning more broadly of having this kind of data sets that everyone works on, and this ImageNet one is the kind of one I was talking about. But there's, I guess, attempts to make more of these kind of shared data sets that people can either use to kind of create benchmarks on or to kind of use for new tasks. I think there are also increasingly tools for doing kind of domain specific tasks. So I'm going to blank on the name now. It'll come back to me in a little bit, but there was recently a computer vision library released, which was for doing kind of page layout detection and particularly for finding tables in images. So, I mean, this is something that people have worked on obviously for a long time, because there's lots of useful information buried in tables which are represented as images. So kind of scientific publications, but also yeah, other kind of sources. And I think quite often what people are kind of moving towards is this idea of transfer learning that I mentioned, where there's either some tool that is already kind of trained on a particular task that you can then just adapt by kind of directly applying that tool or that model. So example from in the kind of text field would be something that predicts named entities, so finds like mentions of people or places. So you might just take a model that someone else has trained and kind of use that as it is. But there's also quite a lot of tools that will allow you to kind of fine tune. So to take that kind of pre-trained model and then you give it, you know, some more examples and it just updates itself slightly to be a little bit more focused on that particular task. So I wouldn't say any of this is properly standardized, but I think there is a kind of move to make those things slightly yeah, more accessible and I guess slightly easier and more efficient to use. Yeah, and I guess yeah, I guess that's one of the slight yeah, the things that I think would be useful in particular domains is to kind of work on that kind of shared understanding and those shared data sets and shared tools. So I think in the, yeah, I guess in the library world, there is kind of work towards that, but I would probably say it's quite early stages really. And I think in some other domains, there's where kind of computer vision and deep learning have been used for longer. I think there's been kind of mixed results. I guess it would be fair to say. So there was a nice paper which I'll add to the document afterwards, which was from the kind of medical imaging setting, and it was, yeah, I guess it was a slightly cynical paper, but it was talking about some of the lack of progress that had been made, even though if you kind of looked at the computer vision deep learning literature, you would think this kind of medical imaging had been completely solved. But actually quite often when you kind of dig into how those tools can be used in that domain in a kind of sensible way, it just doesn't translate, or there's things that have been missed because those domain experts haven't been properly involved in those discussions. So I think that's another kind of, yeah, I guess depending on what domain you're working in, I think that's kind of really important to have that grounding in a domain, or have someone involved in these projects that has a strong grounding in the domain, because I think it's quite easy just to run away with, there's some kind of labeled data set and it seems to give you good results when you train a model, but that doesn't necessarily translate into something useful. I think these ontologies can be they can be quite tricky, and I guess that's with the ImageNet example, I think that was partly because of how WordNet was constructed, that they have some of these things that are a little bit strange as labels. But I guess the other thing that you kind of get if you look through this kind of this list of data sets is these data sets are like often constructed as a benchmark. So sometimes the tasks that they focus on are just ones that are interesting as kind of tasks in their own right. And the things that you might want to do in other kind of settings might be quite different. So I think that's the other slight tension, that something that works very well on this ImageNet might be kind of completely useless at some other kind of computer vision tasks. So I think it would be really nice to have kind of more domain specific data sets that are kind of grounded in tasks that people actually want to achieve, rather than tasks that might be quite useful for demonstrating a particular method works well, but aren't necessarily kind of related to that that particular application.